All right, let's do a second example. We're going to use Moore's circle, and we're given a stress block with both normal stresses and shear stresses. So we have this plane stress situation occurring on a structural member as normal and shear stresses shown here on the stress block. Here we go. Part A is to draw Moore's circle for this state of stress. Part B is to determine the principal stresses and the maximum in-plane shear stresses. And we'll just keep going. So anyways, let's start by drawing Moore's circle. Part A. Step 1 of our Moore's circle process is to determine the center of the circle. And that equals sigma x plus sigma y all over 2, or the average of the two stresses. In this case, sigma x is a negative 3.8 ksi because it's in compression. Sigma y is a positive 9.4 ksi. It's in tension. That's all over 2. So we get a center of the circle equal to 2.8 ksi. It is helpful to know the radius, so we're going to also calculate the radius. That equals sigma x plus sigma y over 2 squared plus tau xy squared, and the square root of all of that. So R equals negative 3.8 plus 9.4 over 2 squared plus the shear stress. It's going to be squared, so we don't have to worry about its sign right now. 5.7 squared, square root of that, equals 8.72 ksi equals R. R is a good one. Okay, so then normally we've just been writing 1 point, but for this problem we're going to do 2 points. So our point is some combination of normal stress and shear stress. We're going to do a right face point. So here, the normal stress is that negative 3.8 ksi. The shear stress is 5.7 ksi, but we have to worry about which direction it's pushing it. So it's 5.7 ksi, and that would rotate this block counterclockwise. Okay, so we'll label the sign in a minute. We're also going to look at the top face, because this will be our sigma. Here we had sigma x and tau xy. Now we'll have sigma y and tau xy. It would really be tau yx, which equals tau xy. So our top face is this 9.4 ksi. And our tau yx is the same 5.7 ksi. Okay, so we have 2 points. We have a center of the circle. So we have more than enough information to draw our Moore's circle. And this Moore's circle is going to be big. Okay, so this axis here is sigma in KSI. And this axis here is tau in KSI. And then we draw our little shear stresses above the sigma axis. We'll rotate that face in the clockwise direction. Shear stresses plotted below the sigma axis. We'll rotate that face in the counterclockwise direction. So here, if we go back up to our tau xy, that's counterclockwise, so we'll be in the negative region here. So we can add a negative sign here, where if we look at tau yx, this is going to push it in the clockwise direction. So this is clockwise, so it'll be plotted positive. So we can plot these 2 points. So we'll start by plotting sigma x and tau xy. So we go negative 3.8, almost 4, and then negative 5.7. So about there. Then we'll plot sigma y and tau yx. So we have 9.4. More than 9, and 5.7. So we're about there. And then we'll plot the center of our circle, which was this 2.8 KSI. So that's about here. And now we draw our circle. Okay, so it's pretty much going through both of those points. Then we can draw a line between our 2 points. That's our plane. Should go approximately through the center. And then we can label our points. So this one up here is sigma y tau yx. That's 9.4 and 5.7. And then down here, we have sigma x, tau xy, and that's negative 3.8 and negative 5.7. Okay, so that's our Moore's circle for that state of stress. Bam! Part A is done. Part B. Determine the principal stresses and the maximum in-plane shear stress acting at the point, and then illustrate an element with a rotation angle at principal stresses. Okay, so we know some things. We know that this is our max principal stress over here. And we know that this is our min principal stress over here. And we know that tau max, this is kind of in the way, so let's see here. See if we can, there we go, okay. Now we have some more room. Okay. So we know that tau max equals the radius, because it's just vertical from the center, which was 2.8. And the radius was 8.72 KSI. So our first answer here is that tau max equals 8.72 KSI, and that equals the radius. Okay, one answer done. Now, let's label what we know. So we'll finish. Oh, we did label this. It's way up here. Okay, so those are all the things we know. Now we need to figure out what this point is and what this point is. Really, all we need to know to do that is that R is this distance, so the radius is here. And the center of the circle is this distance. And also from this point, we have R. We have R here. Okay, so for sigma max, we have sigma max equals R plus C. Let's actually do C. So we start by going from C, so C plus R. So sigma max equals 2.8 KSI plus 8.72 KSI. And we get a sigma max equal to 11.52 KSI. Boom. 2 answers done for part B. Now we want to find sigma min here. So that is just C minus R. So sigma min equals C minus R. So C is 2.8 KSI minus R is 8.72 KSI. And we get sigma min equals negative 5.92 KSI. And we knew that that answer had to be negative just by looking at our Morse circle. It is, and we're happy. So we can label these points. This is 11.52, and sigma min is negative 5.92. So part B is done. Oh, no, it's not done, because we need to illustrate an element with rotation angle at the principal stresses. So to do that, we're going to need more room. So we're going to take all of this to the next page. We need another page. Okay, so bringing all of that over, I'm going to keep using this Morse circle. Okay, so we need to figure out what the angle is so that we can draw the proper orientation. So to go from sigma y to sigma max, we'll go an angle theta. Okay, and theta is on Morse circle, so that equals 2 theta, or alpha is on Morse circle, which equals 2 theta on Morse circle, and then theta is real life. So, first we'll find out what alpha is. And okay. So, we'll find out what alpha is by knowing that this is the radius from this point to this point, and this distance is tau x or tau yx of 5.7. So alpha, so we can do sine of alpha equals 5.7 over the radius of 8.72, and we find out that alpha equals 40.8 degrees. So that is 2 theta. And we want theta, real life. So we divide this by 2, and we get theta equals 20.4 degrees. And so we're rotating sigma y in the clockwise direction to get to sigma max. So that will be clockwise. So to draw our stress block, we start by drawing the original right face. Then we draw the rotated right face. So that's 20.4 degrees clockwise. Then I try to draw this without looking too awful. Okay. All right. And so we label this angle. This is 20.4 degrees. And then we draw our principal stresses. So the key is how to draw them correctly. So to start with, sigma y is what we rotated to get to sigma max. So sigma max will be plotted this 11.52 will be plotted here. So we rotated the top face to get there. So this is 11.52 KSI. One second. Okay. And then the X face will have the sigma min on it. So that will be in compression. So the negative 5.92 is just drawn in compression. And these should be in red because they're our answer. And then all we have to do is draw those equal and opposite on the other faces. So this would be 11.52 going that way and 5.92 in compression. Shear stress equals 0 at principal plane. So that's our answer. So now we have part B is done. Okay, so now part C is to determine the normal and shear stresses on the indicated plane and show these stresses on a sketch. Okay, so we're going to bring this over to a place we can work. These take up a lot of paper space. Okay. We'll delete that. Bring this up here, and then we're going to grab that more circle again because we'll need that. So all of this over here. That looks pretty good. Okay. This is everything we need to do. And get rid of some things that are gunking up our picture a little bit. We already dealt with all of that. Oops. I can't get rid of everything, but we'll make it a little neater. Okay, so here's our original diagram. Now we want to find out what happens when we rotate this X face. We're going to rotate the X face to this to that angle. So we need to find out what this angle theta is. This is theta real world. So theta equals the inverse tangent of 4/5. So we get a theta equal to 38.66 degrees, and that will be, we're going right face to this face, it'll be counterclockwise. Counterclockwise. So on Moore's circle, we have to go to theta, which will be 77.32 degrees counterclockwise. And this is from the right face, X face. Okay, so we're going to go from this point and we're going to travel along 77.32 degrees. And we're going to end approximately over here. Okay. So then we draw a line from that point through the center all the way to the other side, because this will be our new sigma x, tau xy, and this up here will be our new sigma y, tau yx. All right. So we know from before, we knew that this angle alpha was 40.8 degrees. So we're going to label that 40.8 degrees, because that equals this angle, 40.8 degrees. There's a lot of trigonometry in these, or geometry. It's geometry, not trigonometry. Okay, we know that this angle is 77.32 degrees. So then if we take 180, we're going to look from this point to this point, and we subtract the 77.32 and the 40.8, we can find out that this angle here is 66, 61.88 degrees. Okay, so now we can calculate what tau is at that point, because we know the angle. All we need to know about a triangle are two things. We know tau xy, and we know that this distance from here to here is r. So we can say that the sine of 61.88 degrees equals tau xy over r. And we know r, so this is tau xy over 8.72. So we get tau xy equals 7.69 KSI. So this is 7.69 KSI, and tau xy equals tau yx, so this is also 7.69. So that's good. We know two more things. Now we have to find what is sigma x. To do that, we're going to draw a distance here of a. So a, then we can take the cosine of 61.88 degrees, and that equals a over r, which is 8.72. So we get a equals 4.11 KSI. So knowing a helps us, because a equals what this, so if we add c, and a, we'll get to our sigma x. So sigma x equals c plus a, and that equals 2.8 KSI plus 4.11 KSI. So that equals 6.91 KSI equals sigma x. Boom. So this is 6.91. Okay, now all we have left to do is to figure out what sigma y equals. So if this angle is 61.88, that makes this angle 61.88, which makes this tau xy, and this distance a again. So to calculate sigma y, we take c minus a. So sigma y equals c minus a equals 2.8 minus 4.11, and we get a sigma y equal to negative 1.31 KSI. Oh boy. So, last step is to draw this. So we moved, so we need to go 38.66 degrees counterclockwise. So we draw our original X face. Then we rotate that 38.66 degrees counterclockwise. Draw the rest of the block. This is 38.66 degrees. Okay, now we have to get the orientations. Let's start with the X face. So we have a positive 6.91. So let's move this somewhere else. So that angle is 38.66 degrees. So our sigma x is positive. That means it's in tension. And it's 6.91. So equal and opposite on the other side. Our tau xy is below the sigma axis, so it'll rotate that face counterclockwise. So it'll be drawn with the arrow pointed up, making this one the arrow pointed down. Now we could just match our arrows, but we're going to look at sigma y. Sigma y, we found out, was negative 1.31. So that's going to be in compression. (1.31 KSI). It's KSI. And this is 7.69 KSI. And then if we look at this shear stress, is going to rotate it in the clockwise direction. So it will, everything's working out. Our tails are matching and our arrows are matching. And then we draw compression there. Whew, all right. So let's see where we're at on this long problem. We got C done. D, we already know the maximum stress. In this case, it's tau max, which was the radius of 8.72. So that problem is done.